Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering two modules. Now I'm going to record those modules separately. The first module is Module 4, the physical layer, and the second module will be on the binary numbering system, binary, hexadecimal, and the decimal. So we will get to that in just the second presentation in just a few minutes. For now, Module 4, physical layer. Now, if you have any questions, please hold those questions until the end of the presentation if you're here with me live. If you are watching this class as a recording in our NetAcad classroom, please ask your questions in the help discussion forums. And if you're watching this on YouTube, you can make comments down below. I also appreciate it if you thumbs up this presentation and you follow me as well. That would be awesome. Let me go ahead and share my screen to get us started. And I have to do some adjustments here. Start my slideshow. Open the chat room in case some of you want to help me if I get stuck on something. And adjust the screen. Almost there. One more button. Hang on. All right. Module 4, the physical layer. We're going to explain how the physical layer protocol services and network media support communications across data networks. Now, remember, the physical layer is at the bottom of the OSI model. So we start learning about the concepts of the physical layer moving bottom to top. We're going to talk about the purpose of the physical layer. We're going to describe the purpose and functions. We'll talk about the characteristics of the physical layer. We'll identify basic characteristics of copper cable, talk about UTP cable and how it's used in Ethernet networks. We'll describe fiber optic cabling, and then we'll finish with a discussion about wireless media. So we'll start with the physical layer itself. Now, remember, the physical layer is at the bottom of the OSI model. So we learn, in this class, we learn the concepts of networking from bottom to top. So the physical layer, oh great, we have a storm tonight. I can hear the lightning, so hopefully I won't lose you guys. But we'll do the best we can. So physical connection, before any network communication can occur, a physical connection to a local network must be established. This connection could be wired or wireless, depending on the setup of the network. This generally applies whether you are considering a corporate office or a home office, or just a personal home. A network interface card, NIC, connects a device to the network. Some devices may have just one NIC, while others may have multiple NICs, for wired and wireless, for example. And multiple NICs also can serve as backups in case one connection goes down. Not all physical connections offer the same level of performance. Obviously, fiber is faster, say, than some older Ethernet connections. The physical layer. It provides the means to transfer the bits, the ones and zeros. Let me turn on my laser. I can laser whip you guys this way. Ones and zeros that make up the data link layer frame across the network media. So the physical layer is that connection that ultimately sends the ones and the zeros across the network. We'll talk about how those ones and zeros or what they look like in just a moment. It accepts a complete frame from the data link layer and encodes it as a series of signals that are transmitted onto the local media. Encoded bits that comprise a frame are received by the other end or an intermediate device. Now, the other end receives those ones and zeros and then starts the de-encoding process as it moves up the other OSI model. The physical layer, this is the last step in the encapsulation process. The next device in the path to the destination receives the bits and re-encapsulates the frame, then decides what to do with it. I think that should say de-encapsulates the frame. In fact, I am positive that should say de-encapsulate. I'm going to pause this for just a second. Okay, so I went ahead and changed it to de-encapsulate. And by the way, you can use either de-encapsulate or you can use decapsulate, either one that you feel more comfortable with. I think both of those terms are used interchangeably in this class. But the encapsulate, let me go back to the OSI model. So the OSI model, you encapsulate, as we learned last week when we covered models, as you move down, and then it goes across in ones and zeros. And on the other side, it de-encapsulate or decapsulates, whichever way you want to say it, as it moves back up the OSI model on this side. Now, in reality, it only gets to layer 2. Layer 2 will de-encapsulate, look at the data and determine whether or not it's for that device. If it isn't for that device, then it will re-encapsulate it and send it on to the next device down the way. So it's an ongoing process until it gets to the real destination. All right. So, yep. And remember, the PDU is named differently at each layer. So Ethernet frame is the ones and zeros passed along, comes out that that actually the physical layer is connected to. Then you have the IP packet is at layer 3, TCP IP segment, and then user data. That's the stream at the very top. And actually, it's actually layer 3 that determines whether or not it is the right destination, not layer 2. I apologize for that. I'm going to have to redo this video now. Layer 3 looks at the IP address and determines whether it's the correct location. Layer 2 just looks at the MAC address and then determines whether it's the correct MAC address. If it is the correct MAC address, then it moves to layer 3 to find out if it's the right, if it knows about the IP address. If it does know about the IP address, then it's re-encapsulated. If it is this IP address, then it is at the destination. If it is not this location, then it sends it back down, and then the data link and the physical layer, that's what actually in the combination there actually will re-encapsulate it in whatever the next connection is. The next connection could be fiber, or the next connection could be wireless. I hope I didn't confuse you guys. So remember, MAC layer here. If it isn't the right MAC address, it just drops the signal. If it is the right MAC address, it doesn't mean that it's the destination. It just means that it's the right MAC address. Think about a router in a series of routers. It is the right router, but it's not the right MAC. It's not the right IP address. So if it's the right MAC address, that it goes up to the IP address. The IP address says, "Yep, that's me." Then it continues to go up. If it isn't the right one, then it checks its routing table, and then it determines if it knows where the right IP address is. If that's in the routing table, it sends it on in that direction. If it doesn't, it sends it to its default gateway. Maybe I don't have to record it because I wasn't that far off. Okay, physical layer characteristics. This is what we're really talking about. The physical layer down here at the bottom is implemented in hardware and governed by many organizations, including the ISO, the EIA, TIA, ITU, ANSI, and IEEE. You did a research project on that last week, and of course you will want to know which layers of the OSI model are controlled, what organization control those standards before you take the CCNA exam. The TC and then above are covered by other standards, like for example the IETF. Yep. Now, I would say 100% of you here in this class, at least, have a router, a home router that has physical connections. You probably also have a wireless connection on your home router that also not only allows you to connect physical devices through Ethernet, but also allows you to send a wireless connection. Now, you connect a device like a host PC, you connect to one of the physical connections, and then there's also a port that goes to your ISP through their router. Mine connects to a fiber box, and that fiber box takes my Ethernet connection, copper, and turns it into a fiber signal that leaves my house and goes to AT&T. So a network interface card is required whether you have a physical connection or a wireless connection. Remember that NIC has the MAC address, which is unique for that device. Physical layer standards address three functional areas: the physical components, encoding, and signaling. We'll cover them. The physical components are hardware devices, media, and other connectors that transmit the signal that represent the bits. Hardware components like NICs, interfaces and connectors, cable materials, and cable designs are all specified in standards associated with the physical layer. Now, what I can point out there is, for example, when you go on your favorite shopping app that we all shop on almost daily, and you order a Cat5 cable, a Cat5e cable, whatever you're ordering, Cat6 cable, it has to meet the minimum standards. And you may say, well, Don, why is the price vary from a patch cable that might cost $3 to one that costs $30 if they're both Cat6 cables? Well, the standard talks about the minimum standard. It doesn't mean that the corporation that's created business as creating those cables can't add to that standard and make the cable better. Maybe gold-plated connectors, or I don't know what use that would be, or maybe rubber connectors that protect the RJ45 cable from having a loose connection to the cable itself. But anyway, so you can always go higher than the standard, but there are standards that meet the minimum. So when you're shopping online, I won't say you can always just buy the cheapest that you see, but if Cat5 meets the minimum standards of Cat5, Cat6, Cat7, etc. Now, when we're talking about signaling, the signaling is based on the type of medium that we're using. We can use an electronic signal, for example, over copper cable, or we can use a light signal over fiber, or we can use a wireless signal varying the voltage or the wavelength over a wireless signal. All of them ultimately gives us ones and zeros. They all give us ones and zeros. And then they talk about the different ways to encode, encoding, again, converts the streams of bits, ones and zeros, into a format recognized by the next device in the network. So if Ethernet has to be connected to Ethernet, you can't connect an Ethernet cable on one side to a fiber on the other. That just makes sense. The coding provides predictable patterns that can be recognized by the next device. Examples of encoding methods include Manchester, shown in the figure here. So this is a 0, that's a 1, and it's the change that it's based on the change, but yet this isn't a 1. I won't tell you that I'm an expert at this, but this indicates another 0. This indicates a 1. Encoding, it's the method of converting a stream of data bits into a predefined code. Signaling methods of representing the bits. The physical layer standards must define what type of signal represents a 1 and what type of signal represents a 0. Long pulses might represent a 1, whereas short pulses represent a 0. And yet they show us a short pulse here being a 1. So that's why I say I'm not an expert in this. It's really, they're not going to ask you, give you this stream of data and tell you what's a 1 and a 0. They're not going to ask you that question. At least if they do, nobody's told me that they have. So it would be, I should look that up, Manchester. Put that on my list of things to do. Modulation is the process by which the characteristics of one wave, the signal, modifies another wave, the carrier. So here is the carrier signal. Carrier signal is the same. The modulating wave, I wish they had changed it and made 2 different modulating waves, ultimately change the signal to indicate 1s and 0s. Now this is an FM signal and this is an AM signal. They don't actually show you an RF signal for what it would look like in our class. Bandwidth. Now, bandwidth is the capacity at which a medium can carry data. I like to think of it as potential. So think about a highway, and a highway has 8 lanes. That's bandwidth compared to another a 2-lane road or a dirt road. That's bandwidth. Digital bandwidth measures the amount of data that can potentially flow from one place to another in a given amount of time. How many bits can be transmitted in a second? Physical media properties, current technologies, and the laws of physics play a role in determining available bandwidth. Now, it's based on 1 bit per second, and that is the fundamental unit of bandwidth. You have kilobits per second, you have megabits per second, and we have gigabits per second. This is pretty much at home, you're dealing with gigabit per second. That's fiber to the house is gigabit per second. Terabits per second would be more along the lines of major connections between ISPs, and the backbone would be super fast. Many terabytes, if not faster. Latency. Latency is the amount of time, including delays, for data to travel from one point to another. Throughput is a measure of the transfer of bits across the media over a specific given time. And goodput is a measure of usable data transferred over a given period of time. The usable data, the actual data stream. So goodput, you take the throughput, which is the actual traffic that went over the line during a period of time, and you subtract out any latency, and latency could be slowdowns on the network like traffic on a highway, or it could be, and it also removes getting rid of the actually that's not true. Traffic overhead is getting rid of all of the encoding, because all that encoding, the IP addresses and MAC address, all that stuff, that's not the actual data. So you take the throughput, that is what that's what the traffic actually counts for over the line, subtracting all of the overhead, and that gives you goodput. Now we know throughput at home, for example, if you have a cable system at 5 o'clock, it slows down. It's because you're sharing your network with everybody else in your neighborhood. Fiber, I believe, is the same, but I know that when I used to have a dial-up, right? Dial-up was a dedicated connection. You were connected. Granted, it was only at 2,000 bits per second, but it was a dedicated connection. Anyways, that amount of traffic can change based on other people using the same media, the type of traffic you're sending, and latency created by network devices encountered between the source and destination. That every time a router is in the middle of a connection between 2 devices, you have one router, 2, 3, 5, 50, 100, whatever. Every one of those has a moment that adds to the travel of the data frame across the network. Goodput is throughput minus traffic overhead for establishing sessions, acknowledgements, and encapsulation. Copper cabling. Now, really, this is a review of what you learned in your A+ class. I'll go over it relatively quick, but you can absolutely spend more time at this layer and reviewing this material if you want to, and you maybe didn't learn it in your previous classes. But copper, on a copper, we have an electrical pulse. Attenuation is the longer the signal travels, the more it deteriorates. And all copper media must follow strict distance limitations. At this point, I'd like to remind or tell students that at one point, even today, I think it's a Cat 7 cable that I ultimately have. It might be Cat 6. I don't remember exactly. I should go check it out. But I used to have a Cat 5 cable, not Cat 5E, but Cat 5 cable that ran 150 feet from one side of my house through the ground all the way to the other side of my house. That's where my deck is. And I have a router out there, and it helps to transmit the signal to that side of the house and outside when I'm outside on the deck. Well, I used to always have error messages, and I ultimately had a really bad connection. Fortunately for me, I had a possum, and the possum ate the cable. And when he ate the cable, I decided I was going to upgrade that cable. I'm not sure why the possum hasn't eaten my new Cat 6 or Cat 7 cable, but he hasn't. Probably doesn't taste good with all that extra shielding. But ultimately, I don't have any of the problems anymore. And the problem was created. I created the problem because I had that 150-foot run, and Cat 5 isn't good at 150 feet. I think the maximum is 125 feet. That's probably why I struggle to find 150 foot cable. Of course, on the internet you can find everything. And when I ran that cable 9 years ago, I didn't realize the importance of Cat 5E, Cat 6. I don't even know if Cat 6 was available at that point. But attenuation is a real thing, as are possums. Now, you also might have electromagnetic interference. I thought that might be the issue, but it's just running in the dirt around my house. I don't know what would have caused EMI or RFI distortion. Where you see that is if somebody runs a cable, say, in a business overhead, and they run it over fluorescent lights, they're going to, depending on the cable, they're going to run a problem. If you have enough shielding, STP, then you may not have a problem even if you run it over a fluorescent light. But I recommend running it around the fluorescent lights just to avoid any possibility of getting EMI and RFI. Now, to counter, copper cables are wrapped in shielding, and we'll look more at that in a couple of slides. Now, crosstalk is disturbances caused by electric and electronic and magnetic fields of a signal on one wire to the signal of an adjacent wire. Now, that happens within the cable itself, and that's why and I'll talk about that. And again, that's why, for one thing, wires are twisted and they're put in pairs inside of our Ethernet cable. But also, you want to try to avoid running your Ethernet cable with other types of cabling. So at one point, I ran a cable through my attic to my garage. So I have a router in my garage, again, to extend my mesh network. My car is a Tesla, and I wanted to get its updates in a timely fashion. So I put a router out there, a wireless router, and I ran a cable from one side of my house into the attic, over and down into my garage. So I have a physical connection there. And when I was up there in the garage, up in the attic, I was so tempted to run my cable along with all of the other cables that run in my attic. And then I realized I can run Cat 5, Cat 6 cables with other Ethernet cable, but it's probably not a good idea to run it along a power cable with all of the fluctuations in power that probably would create EMI and RFI interference. So I ran that cable all by itself out in the middle of the garage and the attic. And someday people will say, what is this here all by itself for? And there's actually a reason. Oh, I didn't talk about the pictures. This is a pure digital signal, and then what they're showing you here is this is interference. This is just the power that is picked up by your cable over time. And what the problem is that signal interference will lay on top of your pure digital. And now this is really clear. But this is not quite as clear. That's obvious. This is a down, that's an up, this is an up, but it's not clear, especially this last one, for example. And the computer reads this signal, right? So it may not be, here we have zeros and, what's that say there? 036, but it's looking for ones and zeros. Oh, it just shows you one. It got a bit wrong right here because it thought that was a 1, and it was really supposed to be a 0. So anyways, because of this interference up here. They talk about more about copper cabling characteristics, and they talk about the mitigation. So strict adherence to cable length limits, as I was talking about earlier, will mitigate attenuation. Some kinds of copper cable mitigate EMI and RFI by using metallic shielding and grouting, like your coax cable, for example. We'll see that in a minute. And some kinds of copper cable mitigate crosstalk by twisting the opposing circuit pair wires, and that would be our Ethernet cables. So here we have copper. You can see you have a higher attenuation compared to here we have a satellite cable, and here's a thin twin satellite cable. You actually, it's the other way around. So here this has a higher loss because it's a thin satellite cable, and here you have a foil, and here you have a copper ally that allows for less attenuation over distance. Types of copper cabling: we have unshielded twisted pair. We have shielded twisted. Notice that there's shielding on each run of the set of twists. And then here they show the Faraday cable, the Faraday cage, this copper shielding. It's both the shielding and it also serves as ground as well for coax. Now, UTP is the most common networking medium. It terminates with the RJ45 connector. It interconnects hosts with intermediary network devices, like routers and switches. Key characteristics: the outer jacket protects the copper wire from physical damage. Twisted pairs protect the signal from interference. And color-coded plastic insulation electronically isolates the wires from each other and identifies each pair. And the way these are connected to the RJ45 connector is important, and I'll show you that in just a little bit. This is what shielded twisted pair looks like, STP. Not only do you have shielding that shields the individual twists for the groupings, but you also have an outer shielding as well, and then we still have our plastic that performs. Now, the braided foil, this shield, helps provide EMI and RFI protection like the Faraday cable around a coax cable. And then the foil shields for each pair of wire also provides EMI RFI protection. Here they show coax. The outer jacket prevents from minor physical damage. We have that woven Faraday cage that acts as the second wire in the circuit, and it also protects the flexible plastic insulation on the inside. And then you ultimately have the copper connector, which is used to transmit the electrical signals. We've all seen copper, coax, and you've probably made some connectors. There's 3 different types of connectors: BNC, N-type, and F-type. By the way, all of this information is very important for your Net Plus device, Net Plus exam certification, but I really haven't seen too much of it in Cisco. After we talk about it today, we don't talk about it again the rest of the course. So you might have a question or two. Don't spend a whole lot of time on these concepts. UTP cable, that's untwisted pair cabling. And I want you to look at the actual cable itself. I'll zoom in so you can see it. The amount of twists per, I forget if it's foot or meter. Is it meter or foot? Foot, they call it foot. So the number of twists it's clear that this one has more twists than this one. And the reason why you have a different twist pattern is to cut down on that EMI and RFI cancellation between the twists, between the twisted pairs. There are standards, UTP standards for the connectors. The 568, which we'll see in a little bit, talks about the cable type, length, connector, termination, and testing methods. And there's Cat 3, Cat 5, Cat 5e, Cat 6. I know there's a Cat 7. Heck, there's probably a Cat 8 out there. It's just not talked about. And when you're out in the field, you're probably not spending the extra money. If Cat 6 can do the job, you're not going to run Cat 7 or more shielded unless you have a specific reason to run the more expensive cable. Cat 6 does the trick. Here are the connectors. This is what an RJ45 connector looks like. And this is what an RJ45 socket looks like. So if you are setting up a panel, for example, you would be loading RJ45s sockets to terminate on one side of the patch panel, and then on the other side you would have the actual patch cables that would plug into your socket. I thought it was really exciting when I created one of these the first time, and then by the time I did 10, I was tired of it. It does take time and effort to properly create a patch cable, or at least to put a RJ45 connector on an Ethernet cable. If we had this class in person, if you were with me live right now, we would be stopping my presentation and you would be creating some patch cables, because we can always use more patch cables, and you probably need experience at least once creating a patch cable. How do you actually figure out what's connected? Well, it's not random. Based on the standard, you have 2 standards that you may be using in a cable. For example, the Ethernet straight through cable that connects between different devices, like between your PC and a switch. If it's a different piece of equipment, like the switch to the router, then one end would be then both ends would be the same, because you have a straight through cable. Straight through cables connect different equipment, and both ends would be the same. So you would have a T568A on both sides, or you would have a T568B on both ends. Now, a crossover cable is one end is T568A and the other is T568B. Now that's when you connect like devices. So if you are connecting a PC to a PC or a PC to a router, because remember, a router is just a fancy PC, or a switch to a switch, then you would use a crossover. Now, in today's Cisco equipment, auto MDIX is part of each piece of equipment, each routers and switches in today's networking, but it can be turned off. Auto MDIX, and we'll come back to it later, but it will sense the cable type, and it will switch and complete the connection digitally. But you might have a teacher someday that turns that off, or maybe out in the field somebody turns it off accidentally or intentionally, who knows, and then your network can't come up. You'd hate to troubleshoot for hours just to find out that it was just auto MDIX turned off. Now, a rollover cable is Cisco proprietary. That's that light blue cable. We call it a console cable, and it connects a router or a switch to a PC using the serial, or an adapter using a USB connector to a PC. A or B here in the first Ethernet, I'll come back to this straight through. You could use A or you could use B. Now, if you were to quickly do a web search, you would find out that the United States generally uses one, and other parts of the world use the other. Right now, off the top of my head, I'm not remembering which one, but it doesn't really matter as long as you have A on both sides or B on both sides. Your equipment will work just fine. If you were near a crossover, though, it has to be both, and that's obviously why they both exist. Testing it, well, you could do a wire map. You could check cable length. You can do signal loss, check signal loss, and you can check for crosstalk using a tool such as this tool. Now, I would recommend you guys all buy one. They're really inexpensive. I bought one myself for like 25 bucks, and I actually have used it. What you ultimately do, if you have a patch cable, for example, you just plug the two ends of the patch cable into the same device, and it tests the cable. It tells you what kind of cable, what kind of connection you have, and it tells you if all 8 connectors are connected. Now, if you've run those cables through a wall, there's not really a need to, from one room to another, there's not really a need to label them all, because you could, but what if the label gets lost on the way, right? Because what you ultimately do is you take the bottom half of this device and you plug it into the other side. And then on this side, you are testing the signal coming from the other device. It works just the same way. And then you can label all of your cabling on this end after you attach all the RJ45 cables, connectors. Then you can connect it to the right device and label it if you want. By the way, that's how we troubleshoot Ethernet cables that we suspect have been damaged somewhere in the wall. Fiber. So the properties of fiber optic cable, it's not as common as UTP because of the additional expense. It's ideal for some networks and networking scenarios that, for example, require a higher speed. It transmits data or a longer distance at a higher bandwidth than other network media. It's less susceptible to attenuation and completely immune to EMI and RFI. It's light. Why would a electromagnetic signal have an effect on light, right? That just makes sense. It's made of flexible, extremely thin strands of very pure glass. It can either use a laser or an LED to encode the bits as pulses of light. And fiber optic cable acts as a waveguide to transmit light between two ends with minimal signal loss. Up here it talks about it has its positives, but it doesn't have the same kind of protections that that a coax cable has. When it comes to, when I wrote earlier, I said that it had a protective layer. I've taken a shovel accidentally to coax many times in my life. Recently, last summer, when doing yard work, I hit a coax cable, had no problem at all. It just ricocheted all off the cable. And I guess once or twice in the past, I could actually see the metal line inside the cable, the middle, but it wasn't broken. I was able to protect that cable and move on. But in that same yard work that day or over the course of a couple of months, I cut my fiber cable twice. I cut it once, they came out, they fixed it. That shovel just cut right through my fiber cable, like it wasn't even there. In fact, the only way I knew that the fiber cable was cut was my wife came outside and said, "Did you cut the fiber cable? Did you? There's something wrong with the internet." That's what she said. "There's something wrong with the internet. Can you take a look?" I said, oops. That's when I learned AT&T has a really good hotspot connection, because that's how I was connecting to the internet for a month before AT&T came out and fixed that fiber. And then I did it again in a different location. Oh, it was so frustrating. Anyways, fiber, easy to break, but it's really fast and it has great bandwidth, and that's why I pay the money for it. And I didn't have any problem. By the way, AT&T was wonderful. I'm not recommending this, but they didn't even charge me to repair the cable. I guess it's the fiber cable. I guess it's a regular thing. Even the second time I broke it, they didn't even flinch. They were like, "Okay, we'll be out." They did it. Okay. Anyways, somehow you should mark your cables so you know where they are. Anyways, single mode fiber. It has a single single core. It uses less expensive lasers, and it's great for long distance application. The glass core is 9 microns. The glass cladding is 125 microns, so this is not to scale. And then there is a polymetric coating that does not protect it from a shovel, but it does protect it from outside some things. Like, yeah, the shovel, no problem, went right through it. Now there's also multi-mode fiber. It allows multiple paths for the light. The glass core is 50 to 62 microns, significantly bigger than the other picture. Glass cladding is 125 microns, the same. And then the coating is the same as well. It has a larger core. It uses less expensive LEDs. LEDs transmit at different angles and up to 10 gigabits over 550 meters, as compared to just stating long distance applications. So you can get 10 gigabits over 550 meters. Now, the term dispersion refers to the spreading out of light pulses over time. Increased dispersion means increased loss of signal strength. Multi-mode fiber has greater dispersion than single mode fiber, with a maximum cable distance for MMF of only 550 meters. And then they go into a little bit more specific, talking about the specifics. So the jacket protects the fiber against abrasion, moisture, and other contaminants. The composition can vary depending on the cable. The strengthening materials gives you some strength, and it can be the material that's used in bulletproof vests, but not shovel-proof vests. Buffer used to help shield the core and cladding. The cladding is here, and I find it interesting. Again, it's not to scale, because the cladding and the core, the cladding we learned on this slide is 125 microns instead of 50. So that cladding is thicker than the than the inner core. So don't let that be confusing. And then the core itself is the glass. It can be plastic as well, but the glass transmits the light from one device to another. Fiber optic cabling is now being used in 4 types of industry. Enterprise networks used for backbone cabling applications and interconnecting infrastructure devices. Fiber to the home, yay, if you don't have it, you want it. And I saw recently the price is down to like $49 a month or 39 bucks a month. Heck, I used to pay $29 a month for AOL back in the day. Some of you might be old enough to remember AOL. Some of you might still have it in the world. I'm not making fun of you, but when you get fiber to the home, you will be happy. Instead of I don't remember what it was, 2K per second. It's my fiber is 800 megabits per second, and I love it. Long haul networks used by service provider to connect countries and cities, and submarine cable networks used for undersea environments, which can be very long. Transoceanic cables can be very long, and they're protected better than the one out in my yard. Fiber optic connectors. I remember having questions on these devices in my A+ exam. So if you haven't taken A+ yet, you need to know the different devices. It is somewhat important based on the port that you have on your router and your switch. Obviously, you have to have the right kind of connector to connect to your device. And I found it interesting that they are actually, the patch cords are actually color coded, so you can't grab the wrong one. I think the ends are pretty obvious, but I had somebody that was working in the field that says, "Oh yeah, all my patch cables are color coded." Okay. The color coding generally doesn't mean anything in Ethernet. It's just to differentiate maybe different runs, generally speaking. Optical fiber, if you want to compare fiber versus copper, bandwidth, well, UTP, untwisted cabling, is anywhere from 10 megabytes to 10 gigabits, whereas fiber is 10 megabytes to 100 gigabits and faster. Distance, relatively short, 1 to 100 meters, compared to fiber, which could be 100,000 meters in single core. Immunity EMI RFI, we talked about copper is not very immune, where it's completely immune in fiber. Same thing with EMI. The actually running the cable and the cost itself for the cable is pretty cheap for copper, definitely higher expense for fiber. Making the connections can be expensive. I actually found it interesting when I was the second time that I cut the cable, the fiber cable in my yard. It was educational. Not only do I now know where all my cables are, but also I watched the technician and I asked him what he was doing, and they come with patch cables in various lengths. And for my run, it was 200 feet of patch cable, and they run the patch cable from in front of my house to the next connection device, the rebroadcasting for my street, and then from there that goes into a patch cable, patch panel, and then it comes out of that patch panel, and then they run another 200 feet to the next street. That's how they run all the cables. So when I cut mine, they only had to replace the 200 to get from my house to the closest patch panel. Those are those things that are sticking up out of the ground. Those are the patch panels that allow you to have individual patch panels. So I always wondered how, it could be challenging to splice fiber and to make the connections with the connectors at the end. But if you have patch panels and you just have to go from one to another, you don't have to replace the whole line. You just have to replace a single patch panel. And safety precaution, you have to be cautious when you're dealing with fiber optic. Not only do you have to worry about shovels, I think I've worked that humor as far as it's going to go, but you also have to worry about twisting the cable. And I had a cable in my garage. I forget what was wrong with it, but I determined that I could see if I could actually snap the glass in the middle of my fiber cable. And I did. I actually bent down that fiber cable. It's just a short cable I had. I bent it down and then I felt the restriction and then I pushed some more and I pushed some more. And then I don't know if I heard the actual snap, but I could feel the snap when it finally snapped on the inside of that plastic. And so that glass, I finally broke the little glass that was inside there. So you have to be aware of it. Wireless media. Wireless media carries electromagnetic signals representing those binary bits, ones and zeros, using radio or microwave frequencies. This provides the greatest mobility option for your tablets and your cell phones and anything else you're carrying around. Wireless connections, connection numbers continue to increase. The number of things that are connecting wirelessly in my house is amazing. I think if we're talking about the Internet of Things, I think my last count was 42. I think I added 5 more lights in the back. So I think I'm up to about 47 different devices that talk wirelessly to each other. The coverage area of wireless can be significantly impacted by the physical characteristics of the deployment location. When we're talking about 802.11 A, B, G, N, AC, AX, when we're talking about the different standards, they always talk about the standard in a perfect environment with nothing in between, just like when they are talking about your miles per gallon in a car. They're always in a perfect environment. It's never with hills and valleys and traffic, right? So if you have walls in between your wireless signal, and you probably do, you probably have some attenuation of that signal based on what type the wall is, how many walls there are, etc. Interference also causes wireless to be susceptible to things like microwave ovens, for example. Or I once had a wireless problem here in my office where there's enough EMI RFI going on over by my computer that sits to the left of me that I actually had a problem with a wireless signal getting to a device that was on the other side of my desk. So I ran a cable from my router to the device and everything worked fine from that point. So I don't know why it didn't like that wireless, but it works elsewhere in my house. But interference is a thing and you have to be aware of it. You also have to be aware of wireless security issues because you are broadcasting a signal out to the world like FM radio, and then anything out there can pick it up. So anyone with the right device can be gaining access to the transmission and perhaps hacking into your system. Shared medium. Wireless LANs operate in half duplex, which means only one device can send or receive at a time. Many users accessing wireless LAN simultaneously give you different results in bandwidth for each user based on what the other people are actually doing. Types of wireless media. The IEEE and telecommunications industry standards for wireless data communications cover both the data link and the physical layers. In each of these standards, physical layer specifications dictate the data to radio signal encoding methods, frequency and power transmissions, signal reception and decoding requirements, and antenna design and construction. Now, the standards themselves for Wi-Fi, I already mentioned 802.11 and then all the versions of 802.11. Then there's Bluetooth, and there's several different versions of that as well. 802.15, that allows you to have a personal area network. WiMAX, not here where I live, but it uses multi-point topology to provide broadband, basically point-to-point. And Zigbee. Zigbee is low data rate, low power consumption communications, primarily for Internet of Things IoT applications. One of the interesting things about Zigbee is every device, at least I think I understand it to be this way, every Zigbee device is also a transmitter. So the more Zigbee devices you have in your home, for example, my front door lock, my back door lock, and my doorbells, and my thermostat are all Zigbee, and they all transmit the Zigbee signal. So they create their own mesh. And when I called to complain about something with Zigbee, and I was told, well, just add more Zigbee devices or something in between, and it will automatically expand your mesh network. I think it was a backdoor lock wasn't picking enough signal, so they said, get a Zigbee plug for your lamp that's in the middle, and you'll be good to go. And sure enough, I did, and it worked. In general, a wireless LAN requires the following devices: a wireless access point that concentrates the wireless signal from users and connects to existing copper-based network infrastructure. At home, your wireless access point is probably your wireless router. Although you may have access points in the ceiling throughout your home, we definitely have them at the school. And each one of those wireless access points rebroadcasts the signal. Wireless NIC adapters are also required. They are in our network hosts. You have to have a NIC in each device. Remember, it uniquely identifies the device with its own MAC address. That way, our devices can be identified on the network. There are a number of wireless LAN standards. When purchasing wireless LAN equipment, ensure compatibility and interoperability. Don't just go grab a 802.11 B device if you can find it just because it's $9. There's a reason why I spent $400 when I bought my AX router. I don't know if I've used that capability yet, but I needed the newest one, and now I have it. So my future devices will be able to communicate with the AX standard. I don't have any yet, but someday I will, I think, hopefully. Network administrators must develop and apply stringent security policies and processes to protect wireless LANs from unauthorized access and damage. You're going to do a packet tracer on connecting a wireless and wireless LAN. You're also going to do a lab for viewing wired and wireless NIC information. And that is my presentation for Module 4. So I'm going to go ahead and stop sharing my screen. If you're with me and we are live, I'll give you a moment, and once I finish this recording, you can ask your questions. I already see questions inside of the chat room. If you are watching this as a recording, please ask your questions inside the help discussion forum, and I'll be happy to answer those questions. If you're out on YouTube, please like and review the presentation with comments below, and ask questions there too. If I don't answer the question, somebody else I'm sure will. So thank you for coming to class today. I really appreciate it. I will see you again in Module 5 when you're ready for it, if you're watching this as a recording, or in just a minute if you're here with me live. Thank you for coming to class. Have a great week, and I'll see you again soon.